Hi, everybody. Thanks for coming. Sorry for the delay. And anyhow, it's my pleasure to introduce you Wagner Meyer. Wagner is a professor at the Federal University of Minas Gerais. It's in the same city we have a Google office in Brazil, the engineering office in Belo Horizonte. He has a PhD in Rochester and has been working in parallel systems and data mining using parallel infrastructure. And it's always nice to have him around. I always learn new and cool stuff. For once, I've just learned that I should maybe take more time thinking of my idea of installing Linux in my notebook. So, okay. Thanks, Wagner.
Okay. Guess I have a mic. Hello. Hello. Yep. Okay. So, thanks for coming, and it's my pleasure to be here. And I'll try to show you some of the work we have been doing there, not just on the data mining side, but mostly on the parallel computing side. Okay. So I believe that this is quite well known here. It won't take much time here in terms of, okay, so we do have several open problems in terms of internet applications that they're still open, and in some sense they are getting worse and worse by time, okay? So, and these are some of the problems. Data mining, I believe everybody also knows, this is a general presentation. And one thing that's important to note is like there are still several open problems in terms of data mining or what we have to search or patterns to search and so on. Among those problems, we have some application scenarios that are very similar, very related to internet in general. Okay, and these are the ones I will use as a background scenario for our discussion here today. So the first one is spam detection. I guess it's a widely known problem. And the point in spam detection that makes it a bit harder is how it evolves across time. So recently we have a new surge of PDF-based spam dissemination. And then since these patterns, they change from time to time, developing techniques that are able to handle such evolution is not an easy task. Okay, we have document classification, where it's a classic like demand, a classical application for information retrieval in data mining. And again, we can also observe that across time, we do have quite an evolution in those patterns. Customer behavior characterization is the same thing. In practice, we look at more at eBay data and how to detect and formalize what are the interests of the customers, and even information search in social networks, what has been lately quite a challenge for search engines in general. So most of the blogosphere is not really being mapped well by the search engines, and they have quite a hard time finding things there. Okay. One thing that's several factors are common among those applications, and these are the background scenario we are going to use. The first one is that as those applications evolve and the information demands also increase, we can see from the data mining perspective more and more complex patterns to be mined. Several of those patterns, for instance, there is quite a large effort nowadays towards graph-based patterns to be mined. And in fact, there is not really a consensus on what are the patterns and how they should be mined, or even how to handle the complexity that comes when you try to mine such patterns. In parallel, we do have quite a quite significant evolution of those patterns. So even if we are able today of finding what are the interesting patterns, for instance, to mine information from ORCUT, probably in 1 month there will be several different patterns or behaviors that may arise there, and we probably need new techniques, or at least to enhance the existing techniques to grab it. We are, I should emphasize that we are still one step behind, in the sense that for several of the demands, we still don't know what to do in terms of extract information from places like ORCUT. And we do have large volumes of data. And this is also quite challenging, and I believe that you understand this quite well. And in this sense, having techniques that are scalable and efficient is quite a challenge as well. So it's important to see that we have in current techniques and applications, we have techniques that are focused on each of these 3 dimensions. But it's usually hard to find techniques that are that deal with the 3 dimensions altogether. Okay? So either the complexity of the patterns, or how they evolve across time, or being really scalable. And this is basically our background scenario here. So how is our standard modus operandi in this case? So we start by detecting information demands, like these I just presented and discussed, and then we grab real data. So most of our work is based on real data we collected in several places. We evaluate techniques, research novel techniques, and then we work on the scalability and efficiency, and validate through case studies, real case studies. We do support a platform we developed in Brazil that's called Anthill, and it's being used by several government and other institutions for mining data there. And this is a separate effort, but it's one of our motivations for pursuing this. So this is basically an overview of my presentation, and what I focus more is on the scalability and efficiency part, and not on the novel techniques we have been working on in terms of data mining. Okay? And I also won't talk much about the case studies or how the other parts that we perform that are quite standard in this scenario. So focusing on the scalability and efficiency, we just saw that we still have a continuous demand for novel techniques, and we have a scenario that's very clear, that the computational demand tends to increase, regardless just the large volume of data, but because of the complexity of those techniques. Not most, but many of the problems we do have in this scenario, they are well known as NP hard and NP complete, so we don't really have efficient solutions to them. And we usually adopt heuristics towards solving them, and this is quite a challenge. When we look at the dissemination of multi-core platforms and how they are going to increase, then there is also open an opportunity or a challenge for a new level of abstraction in terms of parallel programming. And in this scenario, how to ensure scalability and efficiency. Okay, so that's our strategy here. Well, as expected, we are looking towards parallelizing these algorithms, okay? And there's 2 characteristics that are key to most of the algorithms in this data mining scenario, also applied to those internet applications. The first one is that usually those algorithms, they are quite intense in terms of both CPU and I/O. And this is not really usual for the parallel computing community. For years, they have been working on scientific kernels and parallelizing these scientific kernels that are very intensive from the computational perspective, but not very intensive from the I/O perspective. There has been, in the last 15 years, several efforts towards the I/O, like a scalable I/O initiative and so on. But at that point, they were very concerned about the volume of data, and not in a very intense processing of such volume of data. And this is something that's quite new to the parallel computing community in general. The second thing, and these are also bad news considering the former work we have, most of the algorithms are irregular, completely data dependent or input dependent. So most of the parallel compilers, parallelization compiler techniques are not applicable in this scenario, okay? So we do have a lack of techniques and scenarios that may be applied here. And when we put these two things together, achieving scalability and efficiency in such scenario is quite a challenge. So it's not really usual that you are able to parallelize a technique and make it scale to the tens or hundreds of processors easily, okay? So that's basically our holy grail. What we want is how to parallelize such techniques in the hundreds of processors and keep efficiencies above 80, 90% and so on, okay? Then we have been working in this paradigm for the last 4 years, and we call it the Anthill Paradigm. In fact, this somehow comes from the initial proposal of the anti-iter environment, and it's where it's the kind of a runtime environment where we implement the techniques. There is nothing really, in the sense, completely radical new in the paradigm. But I believe that the approach that showed to be quite efficient and provided good scalable applications and has been applied to several applications I will show later, it may be the best contribution of the paradigm in the environment itself. So the idea is like to decompose the application into filters that communicate through flows. So this is not really new. It's something that goes back to the data flows in the 60s and 70s. And obviously, we are leveraging recent advances in networking technology and this stuff. And by doing this, the interesting part is that we are able to exploit 3 types of parallelism in our applications. And they are the data parallelism in the sense that our filters, we are able to instantiate these transparent copies of the filters that automatically break the data or partition the data among the processes that are participating in this communication. The task parallelism comes into the filters in the sense that a filter, it has a very concise and objective goal in terms of processing. And by emphasizing these, we do have kind of flexibility in terms of where we place the filters and what kind of computation they perform. And we do also exploit, I believe there is an S in excess there. We do have a synchrony there in the sense that we allow all the parallelism that may be exploited to be exploited in the sense that they are restricted just to the data dependency graph of the applications, okay? One thing that's very interesting is by exploiting this asynchrony, as I show you later, we are able to vary the granularity of both task and data parallelism. Because these applications, data mining applications, most of them, they not only are they are irregular in the sense that each, depending on the input data, they behave completely different, but also during a single execution, their profile change. In the sense that they start with one type or one data, like larger data, and then they finish with more tasks and each task handling less data. So to couple with this variability is having the asynchrony, we are able to accommodate all the needs of those applications in order to achieve this scalability, okay? So let me give you an example, okay? So this is a very classical application. That's the frequent Itemset mining, okay? So what we want is giving, before we look at this dependency graph, let me explain the application. In fact, I had a crash in my machine this morning, another crash, and I lost some of the slides, so I prefer to explain this. So what we have is giving a transaction database. We want to determine which item sets or which groups of items occur above a certain frequency threshold. That's called support. So in this case, I'm representing here the search space of the problem of a database that contains 4 types of items, A, B, C, D. And what we want to find is looking at all transactions to find exactly which of those possible item sets are above a given threshold. So and you see that this search space, it increases exponentially, and this is a very popular problem in the data mining community. Okay. In terms of the data dependency graph, the problem works as follows. So basically, we start from single items, exploiting the fact that if a single item is not frequent, none of its descendants will be frequent as well. Okay? So it's a very smart approach. It was developed about 15 years ago, and it's well exploited in the community. So if A is not frequent, none of A, B, AC, AD, ABC, or ABCD will be frequent. And in this way, we are able to perform a quite efficient cut in the search space of the problem and perform a smaller amount of computations. In terms of the parallelizations, we do have some challenge here. So the first one is like, in terms of the large volumes of data, we do have a reduction problem that's implicit to the implementation. In the sense that to know whether A is frequent, you should check its frequency in all partitions of the data set. And the second challenge is kind of a synchronization challenge in the sense that if you have those items here, and when you it's kind of a communication problem to determine whether you may start computing AB, because you should start computing AB just when A and B have been computed, and you know they are frequent. Okay. So previous approaches on parallelizing this problem, they usually they have kind of a reduction, all-to-all reduction at this point, and they become quite synchronous. But the point is, as we go up in this lattice, the number of item sets increase, and the size of the data that should be inspected towards determining whether they are frequent or not reduces. So that's exactly one example of what I just mentioned about that the granularity of the application changes across the execution. So what are the steps? If we look here, okay, page up. So in some sense, we consider as tasks in our approach that determining whether each of those item sets are frequent or not. So these are our tasks, or major tasks. And what we want is to perform this as efficiently as possible and as with the largest scalability possible as well. So what should we do in each case? There is one of the approach that's called the equivalence class approach, and it's based on candidacy. So what's the idea? If A and B are frequent, then AB is a potential frequent item set. If AB, AC, and BC are frequent, then ABC may be frequent. And then the first thing is finding the candidates, then we count the support for each candidate, and then we do the reduction, calculating whether it is frequent or not. There are other approaches that don't use candidates, but I won't talk about them now. So this is simpler to understand than the other approach. So we do have 3 major tasks that are listed here just to emphasize, okay? So this candidate enumeration, that's not expensive because basically what we need to know to do candidate enumeration is which item sets were found to be frequent so far, okay? The second one is knowing that we have to check a given candidate, then we go to all data partitions and actually check what's the frequency of that item set in each partition. And finally, we have to check all this, to sum all these partial counts so that we are able to all the partial counts, so that you are able to calculate the overall count and see the item set is frequent or not, okay? I just make an illustration here of how it works. So we calculate the candidates, send the candidates to the counter, and then the counter what verifies the support. And one interesting thing that's not here because it got missed in my slides crash is like when you know that an item set is frequent, you send back to this set, to this filter somehow so that it may like enable other candidates to be counted. So it's basically a cyclic approach. Why am I emphasizing this here? As you might have noticed, at least the people who are, if there is anyone involved in this, several of the things I'm talking here, they are very similar to MapReduce, okay? And that's maybe the main difference between, at least when we checked MapReduce some time ago, is that in MapReduce, you don't have this ability of iterate and make cycles in the filter graphs. That's one major difference here in the sense that we do store data in each filter and we keep state. So this application is not stateless. The application becomes stateful and we allow all kinds of states to be supported in this case. Obviously, this generates other problems that we must handle, and I'll talk about this later, okay? Going well? Okay? So, in terms of the parallelization, we exploit, being more specific, 2 dimensions, okay? So, first we partition the data set as expected. So we have like several filters, several counting filters, where each filter has a partition of the database. And we have the item set partitioning, in the sense that we have filters that are responsible for particular item sets. That's also a difference in terms of the complexity of the applications. In this case, we have just 2 dimensions, but we have seen cases where we have 4 or 5 dimensions differently. And one thing that we always exploit is trying to keep the scope of a filter to a single dimension. In this case, we are able to do a much easier partition than in other cases, okay? And we do exploit parallelization in both dimensions. In fact, to the time we published this work, this was also novel, because all the strategies so far, they focus on like partitioning either the candidates, either the transactions, or the item sets. And we did both. And both are partitioning in this case, okay? So that's the overall view, in the sense that we merged the candidate filter with the counting filter, and we have like the item set filter over there, and we have like a continuous flow between these 2 filters. It's interesting that when we know that an item set is frequent in the upper set of filters, then we tell this filter that, okay, this is frequent. Since the item set candidacy is a cheap operation, then this guy immediately broadcasts to the other people in the sense, okay, so we start counting these filters, these item sets, and as soon as we learn that these item sets are frequent, we already notify the other filter. That's basically the notion of asynchrony in this case. Let me see if the other slide shows that. No. That's basically the notion of asynchrony, in the sense that as soon as we learn that an item set is frequent, we let the other filter know about that. And then we may start other computations while you are still finishing that counting. So we do have an additional level of parallelism there. So we do have like the communication pattern between these 2 filters, in the sense that from the filter S to C, you tell, like as soon as you learn that an item set is frequent, you send information to all other filters. And from this counting filter, as soon as you learn what's the count of the item set, you send information to the reduction filter, okay? And we use this labeled stream that's it's just a mapping mechanism very close, very similar to MapReduce. Temporarily, I guess both proposals, at the time we published this work, MapReduce has just been published as well. So it's kind of a parallel development we did for some time, okay? So the labeled stream, it's basically a strategy of always sending data related to some piece of information to the same place. So it may be seen as a hash function, very similar to MapReduce in the sense that we, for each label, we do associate a hashing function that will send the data always to the same instance of the filter. And in this case, and why is this very necessary in our case? Because we keep state information in each filter, and in order to have this, exploit this state information and keep the whole application consistent, we need such behavior. But the intrinsic notion here is like we do have a consistent path for all the data that's related to item set AB. We will always go to the same instance of the filter, okay? So what I will do next, any doubts here? Did you understand what's the catch? So being like a short summary would be like, we somehow extended the MapReduce approach to allowing it to have state information within the various processes that are included there. And we exploit the same kind of hash-based addressing between the various processes. So what I will present next are like, this application was one of the initial ones, and after that we performed parallelization of several other applications. And one thing that we try to understand is how the characteristics of the data dependency graph affect the parallelization, or how difficult or easier it becomes, okay? So we divided the several applications according to the data dependency graph using 3 criteria. The first one is regularity. So we do have some applications that are regular and they have been parallelized. A classical example is k-means, okay? So the clustering algorithm that basically what you have to do is you do a reduction to determine the centroid, and then you broadcast the centroid to everybody so that they calculate the next iteration. So it does not depend on the nature of the data. So it basically you do always the same thing, and it's very regular regardless the input, okay? The second one is what we call dynamicity. I don't know if this is the proper word, but anyway. And the point is that there are several applications that you don't know the dependencies prior to the execution, okay? And for instance, in the case of the a priori, the item set mining we just saw, you do know the lattice is determined depending on which are the items that occur inside the data set. But if you pick, for instance, decision trees, you don't know in advance who is going to depend on who in terms of the partitions that are being defined. Because the partitions are defined during the execution. So depending on this dynamicity, this this makes very hard, for instance, to have hashing functions in advance and finding optimal hashing functions that will balance the load in advance, because you never know exactly to where the data will be sent next, and you learn just during the execution, okay? And then we have this last property that's called monotonicity, and it's basically the following. We found some applications that not only the dependence graph changes across you learn the dependence graph across the execution, but also it changes during the execution. So one classical case of this is categorical clustering, Cobweb, for instance, that they build a hierarchy, and they learn about what are the discriminants of this hierarchy. But during the execution, you have splits and joins. So for some time, you have a given node that to which you have to send data, and then suddenly this node vanishes. So that's what we call monotonicity. In the case, the difference between these two is that in decision trees, you don't know in advance what are the discriminants and what will be the partitions, but once you have the partition, it's stable. In the last case, if you don't have a monotonic application, if you have a partition, it may change. And for later in the execution, it doesn't exist anymore. So this gives you quite a problem in terms of implementation. So these are some of our results. So we do have a scenario of various applications, usually various standard applications, where we see the three criteria I just mentioned. Instead of dynamicity, I put kind of a static behavior, so it's the reverse here. The S, oh, I forgot to mention this. Okay, this is one problem. S is yes, okay? Sorry for that. And no is no. This is one of the slides I have to fix before coming here, and I forgot to change the S by Y. So we do have some applications that are very regular, such as k-means, and this is a image analysis application, placenta, okay? And we achieved quite good efficiency in both applications. We do have the application we just mentioned, that's the a priori, the frequent item set mining. Again, we got pretty good efficiency. And then we have some applications, this is the decision tree, okay, where we are not regular nor dynamic. And in this case, it's a bit less, but it's still a quite good efficiency. Then we have one of the most challenging applications we worked so far. And this application, in fact, this application here, it maps to something that showed to be quite challenging. That's doing a depth-first search in parallel in these quite complex graphs that arise from the tree cluster. Tree cluster, maybe you are aware of the bicluster problem, where we want to cluster in 2 dimensions. In the tree cluster case, we want to cluster in 3 dimensions. We add the time dimension to the clustering. And so it basically becomes for each time slot, you have a depth-first search in a graph to find the biclusters. And then you have to find common biclusters across time. That's the tree cluster. So maybe this is the worst result we have here. There is the cobweb, the result I just mentioned to you, where you have splits and joins, and we got a pretty good result as well. There is one last application that I had put before, and it's a different, it's entity resolution. We did a quite large entity resolution, and using a probabilistic record linkage. And we also achieved something like 95% of efficiency, okay? I'm almost finishing. So maybe that's something that may be interesting to discuss here, okay? So what are you doing now? So what are your current efforts in this case? We are really discussing how these filters and flows and so on, how do they will live with multi-core, okay? So this is a discussion we are having, and we are not sure yet what's the response, the answer to that, okay? We do have some ongoing efforts in scheduling. And in this case, one general problem we are looking at is the variable latency. This variable latency, it may arise from simpler things, such as just having machines in different networks to grids, and now back to the multi-core. So one important thing is how to couple with this variable latency in terms of these communications, although asynchrony gives at least an initial scenario to do such thing. And one thing that will also become very important, and we haven't looked much till now, is how to exploit reference locality, in particular in these irregular applications. So it's not necessary that we are completely strict in exploiting this reference locality, but it's interesting that we do as best as possible in order to make the application more efficient. Okay. Then we have the dynamic configuration or reconfiguration of applications, because they change their profile, they change the computational demands. And one thing that we already measure is that we have to come up with scheduling strategies that evolve across time. In the sense that we can just choose a scheduling strategy in advance. And we have to take into account, for instance, the reference locality. And one thing that we are also working is what we call the automatic partitioning. In this case, it's not data partitioning, it's code partitioning. So we want to give in an application to break it into the filters and schedule the filters to the processors, looking for maximum efficiency. Okay? And in this case, there is another dimension, this automatic partition that we want to exploit, is how to make applications to leverage common kernels of processing among them. Okay, so we did find several of those data mining applications. They share common operations. For instance, a very common operation in this set of applications we have here is joins between lists and counts. So these are two common things. Since one of our main goals here is to not move data, but just move metadata and summaries about the data, so this becomes a very important thing. Okay, and also within this automatic partitioning, there is one thing that we also did not work much, but now we have some demands, is how to deal with this trade-off between replication and partitioning. Okay, for instance, the a priori application, we did partition the whole data space, so no transactions are replicated in more than one, like they are replicated in two or more instances of the filters. Obviously, there is a trade-off there in terms of communication versus storage versus the overhead of maintaining this replication information. And this is another thing we are wondering about discussing. Okay, that's something we have been working on somehow. In practice, when we did this last application of the entity resolution, we did really face the problem of replication in that case. Okay, and we had an initial implementation, but it's not generalized yet. That's it. Thank you very much for your attention. I hope I added something to your daily activities.
We have questions. So I have a question.
Okay.
How do you guys deal with fault tolerance? Because the whole problem of keeping state is, you know, if a node fails, how do you recover from that?
Okay. There is a master thesis where we did the first cut on this. Okay. So basically, we employed traditional replication techniques, and then we also did that, like the main problem is like, once you realize that the application failed, you stop the application, you find where to put the program to execute, which nodes are really active, and then you restart the application from the last stable point. One thing that's interesting to mention is like when we look at, for instance...
So I guess my curiosity is more like, how expensive, what's the overhead of keeping those stable points?
It varies a lot. It varies a lot. For instance, in this case, what we had is like, we keep just the item set count for each item set, the global one. And from that, we have like a border from which we start in case of a crash. Okay? There is one thing that's very complicated in this case for sake of fault tolerance, is that these applications, they have very fine granularity. Okay? So this is even worse for sake of fault tolerance, because if we do have a fault and you have a quite fine-grained applications, the amount of data you have to keep is maybe quite large. But the point is the size of the state, it varies a lot. Okay? From very, very small, like state size, such as this item set count, which is pretty small, to having to store larger like portions of the transaction part. That's the expensive part.
So your scheme, you are assuming that the application developer helps you somehow to determine what's the state that needs to be saved. That's not automatic.
Yeah, that's true. That's true. In fact, this interface we have developed for fault tolerance, we created this notion of it was not really state. I just missed the word here. The user has to, we create kind of a tuple space where the programmer puts whatever it thinks it's necessary in this tuple space. And we also created kind of a function, a recover function, that he'll get information from the tuple space and restart the application. Okay? And then we believe that this tuple space is transparent to everybody. Okay?
Transparent in the sense that it's disseminated to all processors?
Yeah. So it's a different part of the system. We just deposit things there, and then we retrieve whenever necessary. Okay? And this is a different problem that we are not tackling now, in the sense that, okay, you do have this stable storage. That's the name we use. So we have this stable storage, and we don't care how you are implementing stable storage. But my algorithms will exploit this stable storage for sake of recovery.
More questions? Okay, so let me thank Wagner once more.
Okay, thank you.